There is an invisible geometric curve so precise, so mathematically exact, that it can be formed from a discarded piece of scrap worth only $9. Once shaped correctly, it unleashes a thermal reaction of such extreme intensity and efficiency that it threatens the entire business structure behind the $170 billion photovoltaic solar market. For years, the public has been conditioned by corporate media systems and utility monopolies to believe solar energy can only be harvested through massive flat panels made from expensive processed silicon dioxide. People were taught that once daylight disappears, those costly rooftop systems immediately lose their value, forcing homeowners into dependence on highly toxic and painfully expensive battery storage systems simply to maintain electricity overnight. According to this argument, that entire framework is built on deception. The real capability of the sun is not hidden inside light itself, but inside concentrated heat. The claim is that true, continuous, 24/7 off-grid electrical generation does not require microchips, delicate wafers, or lithium chemistry. Instead, it relies on ancient optical physics and polished discarded material. The system centers around a precise geometric structure capable of concentrating solar energy into a violent thermal reaction. Advocates describe it as a suppressed technology, now being explored by decentralized off-grid engineers seeking to bypass large solar corporations entirely. Before understanding that concept, the discussion shifts toward what is described as the intentional weakness built into modern solar panels. Commercial photovoltaic panels are portrayed as fundamentally inefficient machines. The public focus remains fixed on the photoelectric effect, where photons strike silicon structures and release electrons through a p-n junction. Yet beneath that process lies a thermodynamic reality often ignored. When sunlight impacts a commercial photovoltaic surface, less than 20% of the incoming energy becomes usable electricity. The remaining 80% transforms into unwanted heat. That thermal buildup damages the silicon structure itself, reducing efficiency while ensuring eventual system failure over time. In this interpretation, the industry considers heat an enemy. Massive amounts of money are invested into cooling technologies intended to reduce thermal buildup on solar arrays. The criticism argues that the industry is actively fighting the same solar force it claims to harvest. The claim continues further. Consumers are allegedly pushed into oversized systems and expensive financing agreements, purchasing 30 separate panels even though, thermodynamically, the kinetic energy striking only 3 panels could theoretically power an entire home if the heat itself were captured efficiently instead of merely converting light into electricity. To explain the scale of this alleged suppression, the narrative turns away from modern semiconductor manufacturing and moves back toward ancient engineering principles. Long before semiconductors or microchips existed, Greek mathematicians and Roman military engineers reportedly understood that solar radiation could be mathematically concentrated. Sunlight was not viewed simply as illumination, but as a dispersed energetic force. By forcing parallel rays of sunlight to converge into one precise focal point, the energy density changes dramatically. Instead of mild warmth, the result becomes an intense localized thermal event. Under those conditions, heavy lead could be melted. Solid timber could ignite instantly, even from considerable distance. Water can be transformed into violently pressurized steam within seconds. The process is rapid, aggressive, and driven entirely by concentrated thermal force. During the height of the Industrial Revolution, this principle of thermal amplification was reportedly used on a massive scale. In the early 1900s, enormous solar-driven steam engines operated across the deserts of North Africa, pumping millions of gallons of water through unforgiving terrain. The systems depended on polished metal surfaces, pressurized liquid, and simple mechanical turbines. They were rugged machines built for continuous operation. According to this argument, everything changed once fossil fuel interests and expanding silicon industries tightened control over worldwide energy production. The mathematical efficiency behind concentrated solar heat became increasingly buried. The technology was inexpensive. It could be recreated inside an ordinary workshop. No corporation could patent the geometry of a curve, and no monopoly could fully control polished scrap aluminum. The steam-powered solar engine was gradually pushed into obscurity and replaced by a fragile photovoltaic grid structure that remained easy to meter and highly profitable. The claim insists that the real foundation of continuous energy generation has been sitting unused in industrial junkyards for decades. At the center of this system is a simple reflective material. A polished aluminum sheet or mirrored mylar film, salvaged at minimal cost, is bent into a precise geometric configuration known as a parabolic trough. The core principle revolves around focal point thermodynamics. A parabola behaves as a highly specialized optical structure. When parallel sunlight enters the reflective interior surface, the laws of specular reflection force every ray toward one exact central axis, regardless of where it initially strikes. The result becomes a passive channel concentrating massive thermal radiation into one narrow region. This is presented as the hidden mechanism behind the $9 concentrator. While a standard $15,000 flat solar installation absorbs only a diluted portion of incoming sunlight, the parabolic trough gathers a much larger physical field of solar radiation and compresses that energy into an intensely hot focal strip measuring only 2 inches. A simple copper plumbing pipe rated for high temperatures is then positioned directly along that focal line. The pipe is coated matte black to maximize heat absorption mathematically. Under those conditions, the process shifts away from weak, low-voltage direct current production and moves into phase change thermal transfer. Water or automotive coolant circulating inside the copper tube becomes flash-boiled almost instantly, creating highly pressurized vapor through concentrated solar heat. The explanation then transitions into a mathematical breakdown called the thermal magnification quotient. The equation is described as total thermal magnification equal to the massive aperture area of the curved reflective surface divided by the extremely small area of the receiver pipe, multiplied by the raw direct normal irradiance of the sun. Attention then turns toward the economic comparison with conventional photovoltaic systems. To operate an average off-grid home using standard solar infrastructure, a minimum 10 kilowatt photovoltaic array is required. The silicon panels, proprietary aluminum mounting hardware, and vulnerable microinverters carry a combined cost of roughly $15,000. However, once sunlight disappears, electrical generation immediately falls to zero. Maintaining power overnight requires an additional lithium-ion battery wall costing another $10,000. That places total capital expenditure at $25,000, while the entire system continues degrading year after year until failure becomes unavoidable. The narrative then shifts toward what is described as a decentralized thermal kinetic alternative. The example focuses on a documented case involving an off-grid welder working deep inside the harsh landscape of West Texas. Frustrated by aggressive pricing from corporate solar contractors, the welder abandoned the conventional silicon system entirely. Instead of signing expensive installation agreements, he traveled to a nearby industrial scrapyard and purchased 6 discarded aluminum commercial lighting hoods, along with several rolls of reflective adhesive mylar film. The total cost reached only $54, equal to $9 for each reflector assembly. Using basic geometric calculations, he manually shaped the recovered aluminum into accurate parabolic troughs. The inner surfaces were carefully lined with the reflective film to maximize solar concentration. Standard low-cost copper plumbing pipe was then suspended directly along the precise focal axis of every trough. He linked the pipes together into a sealed circulation loop and filled the system using a $45 combination of distilled water and high-temperature automotive antifreeze. The superheated pressurized loop was routed into a heavily insulated, salvaged residential water heater tank. That large water volume functioned as a dense thermal storage battery. To complete the system, he attached a modified salvaged automotive turbocharger operating as a compact steam turbine. The spinning assembly drove a standard high-output truck alternator. Beneath the relentless heat of the Texas sun, the $9 scrap reflectors concentrated solar radiation with extreme efficiency. The liquid moving through the focal pipes rapidly reached full phase change temperatures exceeding 400 degrees Fahrenheit within minutes. That superheated fluid continuously charged the insulated thermal reservoir. As the pressurized vapor expanded through the system, the turbine kept rotating at high speed, producing large quantities of stable electrical current. But the most significant engineering advantage appeared after sunset. Because the energy was stored as concentrated thermal pressure inside an insulated water tank, rather than fragile lithium chemistry, the salvaged turbine continued spinning throughout the night without interruption. The dense thermal mass inside the insulated tank reportedly retained concentrated heat for more than 18 continuous hours. With an initial investment below $300 in discarded metal, common plumbing hardware, and salvaged automotive components, the welder achieved continuous 24/7 high amperage electrical production. The system bypassed the need for $15,000 silicon panel installations. It also eliminated the requirement for a $10,000 lithium-ion battery wall. According to the narrative, the economic efficiency of this arrangement directly challenges the centralized utility structure. The welder achieved long-term localized energy independence using discarded industrial materials. The argument continues by claiming energy monopolies depend heavily on the illusion that solar harvesting is an ultra-complex technological process, manageable only by authorized specialists. If ordinary people recognize that polished scrap metal bent into the correct mathematical shape can boil water and drive turbines through the entire night, the financial foundation of the photovoltaic industry would collapse rapidly. The geometry of the parabola is presented as a direct challenge to energy monopolization. Unlike digitally managed systems, the process relies entirely on mechanical physics. It cannot be remotely disabled through smart grid software updates, and it cannot easily be controlled through centralized metering systems. The claimed future of localized off-grid power does not involve financing increasingly expensive internet-connected solar products from major corporations. Instead, it involves recovering discarded industrial metal, polishing it into reflective surfaces, and applying the same geometric principles ancient civilizations once used during the rise of massive empires. The narrative closes by claiming that additional historical archives remain hidden, including a suppressed 1912 blueprint said to multiply localized power efficiency even further. It also promises exposure of planned obsolescence inside modern solar inverter systems built around fragile microchips and vulnerable electronics. If this breakdown of concentrated solar thermal systems challenged what you thought you knew about energy production, stay with us for the next chapter. More hidden engineering concepts, historical designs, and overlooked mechanical systems will be uncovered next. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.